Good day, I'm Maile Matsiba. Welcome back to our channel. Today we're continuing with our SWK 210, which is the strength of material from the University of Pretoria. We continue with our chapter 1, and today we're looking at problem 1.7. There's a sketch right there, and the question says each of the 4 vertical links has an 8 by 36 millimeter uniform rectangular cross section, and each of the 4 pins has a 16 mm diameter. Now the question is, determine the maximum value of the average normal stress in the links connecting A, B and D, and B, C and D. So let me just explain and show you guys the 4 links. This is the first link, and behind there's actually another link. So this structure you see, I call this, like this sort of a beam you see here, it's actually seated between 2 links, exactly the size. One here as you see it, but the one you can't see it, I just drew a line here to show that actually behind it there's another link, so it's seated behind it, and it's actually held together by a pin here, and exactly and that happens again also exactly here. There's one link here, another one here, and then they are held by a pin. Now what's happening here is exactly also happening here. There's also another sort of a beam here, and it's seated between these 2 links. It's also held by a pin here and by a pin there. Now that's why they say each of the 4 vertical links has an 8 by 36 millimeter uniform rectangular cross section, which basically means that this is actually an 8 by 4. Remember, it's a link, so here it will be a typical 36 millimeters, but now because it has some thickness, that thickness would be 8 millimeters. So, and they are all the same. Now it says that each of the 4 pins has a 16 millimeter diameter. So there are 4 pins, 1, 2, 3, 4. Each of them has 16 millimeters diameter. So now with that said, they say determine the maximum value of the average normal stress in the links connecting B and D and also connecting C and D. So we're going to calculate the average normal stress in these links, the links connecting B and D. On question A, we're going to calculate the average normal stress in the links connecting B and D. And then in our second question in B, we're going to calculate the average normal stress connecting C and E. Now, for us to move further from here, we have a structure there. Now we need a free body diagram. So I'll just draw one here. So, okay, I forgot to mention here that at this point, there's actually a 20 kilonewton force that is applied upwards at this point. So when we have that, then this will be our 20 kilonewtons, and the B and D, I'll just put it like this. I will explain later. So this will be our force in BD. Yeah, this is force in BD because remember, these are held together. When you push here, there will be a force applied here, and also there will be a force applied there. Now with that said, we can just say, put another force here and say it's force CE. So now we have our 3 forces there. Then we just also put the measurements. There's 0.025 meters, so it's gonna be 0.025 meters, right? And from here to there is gonna be 0.040 meters. So that is almost our free body diagram, or let me just name it A, B, and C, right? So yeah, that is basically our free body diagram. Now when we have our free body diagram in this way, normally, or the easiest approach for us to be able to determine the maximum normal stress, we know we're gonna need the forces, right? If we're going to calculate the average normal stress in BD, we're gonna need FBD, right? So the first thing we're going to be doing now is to calculate FBD. And for us to do that, it's easier for us to calculate the sum of all the moments at point C. This is typically, I think it's 122 SWK 122 work, where we know that we have two unknowns. So if we calculate the sum of all the moments here, we're going to eliminate FCE, and we're going to have a known force and an unknown force, and it's going to be easy for us to get that. So with that said, we can just say, therefore, sum of all the moments, let me say, sum of all the moments at C is equals to 0. Now, if sum of all the moments at C is equals to 0, therefore, BD from here, from B to D is 0.04. So we're just going to say 0.04 multiplied by BD. So it's going to be, and remember, another thing I need to highlight is that if it's anti-clockwise, it's positive, and if it's clockwise, it's negative. So with that said, we know FBD, if we take the moment by C, it's going to be anti-clockwise, so that makes it positive. So we're going to have 0.04 multiplied by FBD. Now with that said, we need to also calculate, we need to also calculate 20 kilonewtons, the moment of 20 kilonewtons by point C. And with that said, because now when you look at the 20 kilonewtons, it's gonna go clockwise, it's negative. So we're gonna say minus 20 times 10 to the power 3, that is the force, multiplied by, now the distance is gonna have to be the total distance. So you can just say 0.025 plus 0.04, right? And all this is gonna be equals to 0. Now with that said, if there's only one unknown, which is FBD. So now if you do your calculations, you'll find that FBD is equals to 32.5 kilonewtons. So it's 32.5 kilonewtons, so your 32.5 times 10 to the power 3 newtons. So that becomes our FBD. Now we got our FBD because we took a moment by C to eliminate FCE. But now we need FCE. And for us to get that easily, we can easily eliminate FBD, and then by taking the moment by B, we can, now that we have FBD, we can also take a moment by A, but I think it will be much more straightforward if we take a moment by B. So we say the sum of all the moment by B is equals to 0. Therefore, now we can start with the 20 kilonewtons. Is gonna, from here, is gonna go clockwise, and that makes it negative. So we're gonna have minus 20 times 10 to the power 3 multiplied by the distance from A to B is 0.05, right? Now do the same with FCE. It's also going clockwise, so we're gonna say it's gonna be minus FCE multiplied by the distance from B to C is 0.04 meters. So all this is equal to 0, and we only have one unknown. And if you do your normal arithmetic simplification, you'll find that FCE is equals to minus 12.5 kilonewtons, right? And another thing I need to highlight this here is that now we need to remember these two links can either be in compression or in tension. So one thing that tells us about either a link is actually in compression or in tension is the sign of the force. So now FBD is actually positive, and if it's positive, that means that link BD is in tension. So that means link BD is in tension. Why? Because the force in BD is actually positive. So I can even write it in here and say FBD is positive, just so that it can be visible. So also now FCE is negative, then that tells us that FCE link CE is actually in compression. Why? Because of the sign. So I can just say here that link CE is in compression, right? And say FCE is negative. So now this is the first part. We are done with the first part of our question where we calculated the forces. So now we are almost halfway there. Remember, the question says they need the average normal stress, and we know the equation of the stress is it's actually force over the cross-sectional area. So now what we need now is to actually calculate the cross-sectional area, which is something very much important and something very much interesting, especially the portion or the part that I'm going to be explaining. So now we're gonna start with link BD and calculate the cross-sectional area. So we can just say area, or let me say that cross-sectional area, cross-sectional area of link cross-sectional area of link BD is equals to, I just needed to write that sentence there. I could have easily said area is equals to, but I wanted to just write that is equals to. Now I need to explain something here. There's a very interesting difference between the cross-sectional area of the link that is in tension and also the link that is in compression. So now the link that is in compression, let me just write it down and then I'll explain it. Is equals to, we know that that's the length, right? Not really the length, the thickness. We know the thickness, and then there's also the length. So we're gonna just say 0.008 meters, right? Which is the thickness. Remember, we are told that it's actually an 8x36, right? Multiply by. Now, instead of using the whole 36 millimeters, we're gonna say 0.036 meters minus this is actually where I need to explain this. Okay, let me just write this properly. Now, when a link is in tension, the cross-sectional area that you're actually using is actually let me just draw a line here. It's actually, remember, the cross-sectional area is gonna be, the area here. I hope it's visible. So now when a link is in tension, this area here that is actually occupied by the link, it's actually not counted, which means you get the area from here to here and then jump the hole or the link from here to there. And this is basically because when you take, I hope that will be much more clearer in explaining, when this link is in tension, this pin here is actually pushing upwards, and as such, in pushing upwards, the only other, actually at this point, how do I explain that? This is actually, I have something in my mind and then I'm trying to explain, but I'll find a way of explaining it easily. The thing here is that I could easily say when the link is in compression, when the link is in tension, you minus this area, and when it's in compression, you add it. But the y part, I'm trying to explain the y part. Why is it that we have to minus that? That is actually what I'm trying to present to you guys. And this is because practically when when this is in tension, the pin actually is actually moving in that direction. And with that said, this part, only this part and that part is the one that is actually affected. Why? Because remember we are calculating the average normal stress. So which means, or rather, the maximum value of the average normal stress, which means the highest normal stress that this pin in tension can actually take is the normal stress that this part here can take. I hope that is much clearer. And this is because that if the pin rather experiences a tension or a stress that is actually much higher than this part, it doesn't really matter if this whole part can handle it. As long as it can experience a stress that is higher than this part, then this pin or this link will actually fail. So yeah, but I'll find a much better way of explaining that, and I hope it will make much more sense. But the thing is, when the link is in tension in this case, the area here has to be, subtracted. And yeah, and because we know that the diameter of the link is actually 16 millimeters, so we can easily just say minus 0.016 meters. So then that becomes it. And with that said, you get, when you use your calculator, then you get it's 0.00016 meters squared. So yeah, that becomes your the cross-sectional area of this pin. And can I just draw it here? Let's say I cut this pin here, right? This is actually what is gonna I'm gonna just try see if I can give you like a 3D. Yeah, this is actually the pin. So this shouldn't really matter. So if I cut this pin, if I cut this by half here, I'm gonna be left with this. So the cross-sectional area that is actually being calculated is this area here, and excluding the place where there's the pin and this area here. And that's why when we calculated the cross-sectional area, we did say your 36, right? We did say 8, and then 36 minus this part here, which is the 16. I hope that's much clearer. But there's more. With time, I'll find a better way of actually explaining why, because the important thing about this module is knowing the why part of things, not necessarily knowing how to solve it, because it's much easy to solve it, but if you know the how part, then the tricky part of this module will actually be much more easier. So yeah, with that said, now when we have that area, then we can actually, then remember, we have that cross-sectional area, we calculated it to be 0.00016 meters squared, but there are two links, right? So it's this link and the one at the back. So if we go, the force BD is actually acting upon both the links. So with that said, the total cross-sectional area that BD is actually acting on is gonna be twice that. So we can just say area or cross-sectional area for two links is equals to, you can just multiply that by 2, and then it's gonna give you 0.00032 meters squared. Now that we have our area, cross-sectional area of the link BD, which we have already established that is in tension, and we also have the force BD, then we can answer the question A that says determine the maximum value of the average normal stress in the links connecting A, B, and D. And that is easily, we can just say A, we say average stress of BD is equals to FBD all over area of BD, right? And we already calculated all the values we need. We know the force BD is equals to 32.5 kilonewtons, so it's 32.5 times 10 to the power 3 newtons all over the cross-sectional area of link BD, this is it. So it's gonna be 0.00032 meters squared. And if you use your calculator, it will give you 101.5625.00 pascals. Right? Now, if you're gonna convert it to megapascals, so it's gonna be equals to 101.563 megapascals. Now, with that said, we have answered question A of the problem. So now we're going to question B. Remember, we answered question A. Question B is always similar. It's also similar, but now we're gonna use the values of CE. Now, with that said, remember here now we only have the force, but we don't have the area. So the first thing we needed to calculate is actually the cross-sectional area of link BD. However, link BD is actually in compression, and because we've established that because it's negative. Now, when the link is in compression, we use the whole cross-sectional area. And I'll also again attempt to explain that, but this one is not so complicated. So we can just say the area of CE is equals to it's equals to 0. Let me use the meters. It's equals to 0.008 meters multiplied by 0.036 meters, I think. Yeah. So, and if you use your calculator, it's gonna give you 0.0000288 meters squared. However, this is also in the same way with the first question. This is actually two links. Is the first cross-sectional area here and the other cross-sectional area of the other link at the other side, because this force is acting on both links. So we can just say that the area CE for two links is equals to, when you multiply this by 2, it's gonna give you 0.0000576 meters squared. Now, with that said, I need to explain the issue of why is the in compression we do that. So I'll go back to the same here. You see, in tension, when this whole part is actually pushed, okay, let me say this. For the link, for the for the pin to be in tension, it has to be tight, it has to be held by both sides. In as much as it's pushed up, for it to be in tension, it has to also be pulled down, right? And that is what will actually create tension on the pin. But in this case, it's only these links, because they are held here and there, that are actually experiencing the tension. The link itself, it's not. So the area of the link does not count. However, in compression, when you actually compress this, let me just put in the pin here. If this is a pin here, right, and you actually exert some pressure down, there's some force here and there's some also force here, right? Not just on the link, but also on the pin. And as such, because also this, which means this whole area here is actually experiencing compression. Whereas in the case of BD, this whole area, only this area was experiencing tension, because the pin here was only held in one side. I hope that makes sense. This is actually just one of the principles of physics that I believe with time, especially along this course, it will develop. But that's very much important, especially because this module is full of tricks in itself. So that's why I always try to emphasize or explain the how part of things, because if you know how the how part of things, if in one way or the other the module or the question surprises you, you can always find a way through solving that. So that is it. So now we have established the area of CE, the cross-sectional area of CE. Now with that said, then we can go answer the question on determine the maximum value of the average normal stress in the links connecting C and D. And now that we have all the values, we can simply say the stress of CE is equals to the force CE all over the cross-sectional area of CE. Now with that said, we know the force CE is equals to it's minus 21.5 times 10 to the power 3 newtons, right? All over the area, the cross-sectional area of CE is 0.000576 meters squared. And if you use your calculator, it should give you, let me just verify here. It should give you minus 21.7 times 10 to the power 6 pascals, and that is equals to minus 21.7 megapascals. So with that said, this brings us to the end of the question, and I hope I've really managed to explain what needs to be explained, but I think I've touched enough blind spots in this question, and with time along this module, eventually it was going to be much more easier for everyone to grasp it. But I believe by now it's much more easy. I think this is very much easy. The challenging part is just finding the area, because if you can't find the area, the correct area, then that kind of like messes up the whole thing. But if you find the area, then everything else that's left becomes only the mathematics. So thank you guys for your time. Stay blessed, guys, and I love you.